Hi and welcome to my first video of this channel. My name is Alwas Alsandi and I am going through each homework lecture and seminar task for the biochem topics. And today we're going to focus on the liver and its function, but also xenobiotic metabolism and the homework related to that, and then we're going to discuss seminar tasks together. I am notice right now that, or I try to notice to you guys that I'm a medical student, so I don't have any type of degree, so I will sometimes say some things that are wrong, so just correct me in these cases. And I do these videos because I try to learn and also share some help with you guys, maybe try to understand these topics easier. So the first task of the homework lecture was to write down these enzymes and related to each enzyme class or each macromolecule they are related to. And I don't need to go in deep for this one. I just basically because we've already talked about many of these enzymes, so arginase, we know it's part of the urea cycle, so it has to do with protein metabolism, and also arginosuccinase synthase, also one of these urea cycle enzymes. And same thing with the glycogen synthase, aldolase B, glucose 6-phosphate dehydrogenase or glucose 6-phosphatase, galactokinase, and many enzymes also related to these ones. So I just wrote down, you guys could screenshot this, write it down on your own table, free feel to do whatever you want. But what we was supposed to do was we should write down the major consequences of this enzyme deficiency. And so I'm not gonna 100% go through them all because it's just gonna take forever and I'm just gonna overwhelm you guys with information. So I will try to explain for each macromolecule and its deficiency what it could be do, but also I will try to maybe name one of these two enzymes. So let's talk about the carbohydrates. So we have been given fructokinase, so it says that fructose is increased in the blood and there are no symptoms. But I could also talk about aldolase B. So this aldolase B is called hereditary fructose intolerance. So we can't really, because fructose 1-phosphate in the next step by aldolase B is making, I think, dihydroxyacetone phosphate, and also I think glyceraldehyde 3-phosphate, and these steps could either join gluconeogenesis or glycolysis depending on the state of the body. But if you have a deficiency, let's say then in this aldolase B, this means that when you eat fructose, you will be able to break it down to fructose 1-phosphate. And even if you eat high amount of fructose, you will get a high accumulation of fructose 1-phosphate because you can't really break it down because you have a deficiency in aldolase B. So this will irritate your immune system and you could start vomiting, you get abdominal pain, and also severe hypoglycemia because you can't really use sugars to create energy. And this will also then deplete gluconeogenesis. So in fat states or fasting states, or when we have glucagon that dominates the bloodstream, we can't really create energy from it. So basically, accumulation of sugars, which could lead to hypoglycemia, is mostly related to carbohydrate metabolism. Also, we could talk about fat. So let's go to the fat ones. So pathology is related to fat metabolism. Like carnitine acetyltransferase, we know it's one of the most important enzymes for transporting acetyl coenzyme A to the inner mitochondrial membrane, so we could then proceed with beta oxidation. So if you don't have that, so let's just say during fasting state, we can't really produce energy once again, which could lead to vomiting and hypoglycemia and other diseases as well. And if we have deficiencies in arginates or any enzyme related to protein metabolism, we could get accumulation of ammonia. And ammonia is toxic. When it accumulates, it could lead to mental retardation and also decreased in pH. So we really try to get rid of ammonia. But if you have enzyme deficiency, then you can't really get rid of ammonia, and ammonia will be accumulated and it's just have toxic symptoms for us. So this was just like, I can't really tell you guys so much about this, because I think this is just recognizing the the enzymes and related to each metabolism. And I also know that maybe I've missed some of these enzymes as well, but the main idea is to at least like cover the most of them all. And the next task. So the next task is talking about liver detoxification, acute phase 1 and acute phase 2. So we should talk about which reaction and enzyme or cofactor are like active in each phase. So we basically, what we have is, if we have a toxin, so this could be paracetamol, or it could also be benzopyrene epoxide, benzopyrene epoxide, I think it's called. I don't 100% remember, but so it could be any type of toxin, any type of xenobiotica. So what happens here is that we have in the first phase, we could use enzyme from cytochrome P450. Basically, we try to make the substance more water soluble, and then we conjugate it so we could then excrete it then through the kidney and urine. So the first step is we try to reduce it, oxidize it, hydrolyze it, maybe hydration type of reaction. And we need then these cofactors, because we know that niacin, pyridoxine, folic acid, riboflavin, niacin is important for oxidation and reduction and hydrolysis reaction. So this is just purely theoretical and nothing like so interesting. But right now, we made this toxin maybe a bit more water soluble. The next step is we conjugate it with the last groups. So it could be sulfation, conjugation, acetylation, and then we make it like the most possible form of water solubility, and so we could excrete it through the kidney and urine. So I will give you guys, like, for example, so the enzymes which could be used are glutamine, taurine, glycine, ornithine, and arginine. So let's just take a quick example of glutamate. So what does glutamate do? Glutamate with cysteine creates glutamyl cysteine, and glutamyl cysteine with glycine creates glutathione. And this glutathione molecule right now, what could this glutathione molecule do, like in general? This glutathione molecule, as we see here, when we have paracetamol, so it contains acetaminophen, like around 80% of it could be excreted through the kidney and the urine, just simply as it is. But we have 5 to 10% that can't really be excreted, or is still left. So CYP to E1 is degrading this acetaminophen to NAPQI. And this NAPQI is very, very, very toxic. And in case of overdose, we could get cell necrosis, so which means cell death in the liver. So then, because we need this glutathione, we can then use this enzyme to create mercaptochloric acid and then secrete it through the kidney. And this mercaptolic acid are less toxic than NAPQ1 are. So don't overdose on paracetamol. And yeah, this was just to showcase why we needed, for example, then glutamine and glycine as an example, as I showed here, because we needed glutamate and glycine to create this glutathione. And this glutathione, in the reaction for the conjugation, is important. Now, I think I missed one of the pictures I wanted to show, which showcased that now when these glutathione bind then to this toxin, we will create it like in the most soluble form, and then we could excrete it. Okay, and then this is also just pure theoretical, like just write down. I think also I may have missed some of these enzymes and cofactors, but yeah, whatever. Like, I think the most important thing is to catch the main idea here. Okay, so let's go through this one. So in this scheme, you will see one metabolic pathway that takes place in the liver, and we should recognize it and name a substrate, and yeah, try to draw them yourself. No, I'm not gonna draw them because when the school asks us to draw something, because now we've done, I think, around 4 colloqs, and never in one colloq did we need to draw any molecule, but they said to us that we need to draw them because it helps us personally with recognizing the structure, which in the colloquium we get metabolic pathways with just plain molecule structures. So you guys could draw them if you want. I'm not gonna personally do that because it's just time consuming and everything. So what are the molecules? So you have firstly ethanol with alcohol dehydrogenase creating acetaldehyde. And this acetaldehyde in the cytosol will then, by aldehyde dehydrogenase, create acetate. And then this acetate could go to the circulation, and from circulation there could be creating acetyl coenzyme A, which could then, for example, be forming ketone body in case of starvation or entering just a citric acid cycle. And I will right now talk in short of the consequences of this molecule intake. So this is the ethanol. So what happens when we take ethanol? So ethanol intake leads to increased NAD and NADH ratio, which could lead to metabolic acidosis, and the ETC is inhibited. And you could ask me why. So as you can see here, we have increased NADH. Here, NADH, and here also NADH is increased, right? So this molecule right here and this molecule right here. This will lead that we have an increased NADH production. And what could this do then? So what this could do, I know maybe in the picture is not showcased good. That was not good. But I will theoretically then explain this to you. Oh shit, what happened? Okay. Sometimes my iPad is disrupted. So basically, because when we have so much NADH, we want to use this NADH to create from pyruvate lactate. And this lactate will be increased because we want to regenerate NAD+. So when this lactate accumulates in the body, you know what this will do. It will lead to a lactic acidemia, so basically a drop in the pH level. And this also drop in the pH level and this accumulation of lactate, this could then interfere with uric acid production. So we won't excrete uric acid in form of urine, which will lead to accumulation of uric acid, which we know would lead to the gout. So basically, accumulation of uric acid in form of crystals in the tendons, and yeah. And this could also then inhibit, or what will this also do, that oxaloacetate in the citric acid cycle will be going through a reaction creating malate, because we want to regenerate NAD back. So if we don't have any oxaloacetate, then acetyl coenzyme A can't really bind to anything. So we can't really use ETC, and also gluconeogenesis is also inhibited in this case. So ETC and gluconeogenesis is inhibited because what can we do in this case? We can't really do anything because the ETC cycle are inhibited because oxaloacetate are being reconverted to malate because of the increased NADH production by ethanol. So ethanol leads to increased NADH, which could lead to metabolic acidosis, and ETC is inhibited because oxaloacetate are formed to malate and pyruvate are also formed to lactate. Yeah. Also, because also one of the other like toxic effects of ethanol is that ethanol, when first reaction happen, is we create by alcohol dehydrogenase, we create acetaldehyde, and this acetaldehyde could do many of these things. One of the things is that it could bind to these protein clotting factors and inhibit clotting factors. So in case of cell damage, or in case of hemolysis, then the cell can't really use clotting factors, and we can't stop bleeding, so it will just lead to internal bleeding. But also it could bind to this glutathione, and this glutathione by the acetaldehyde is like so by alcohol abusers, so the people who just drink alcohol a lot every time and every day, which this could do because glutathione are really used like a lot because of it's because also this was I wanted to showcase. So when we create acetaldehyde, this reaction here, when we create acetaldehyde in the microsomes, also we have this reaction happening by CYP2E1, and this is basically like we using this enzyme with glutathione. So glutathione here, glutathione is defending against these reactive oxygen species. So these reactive oxygen species, these radical, are being reduced by this glutathione, but we are using glutathione so much because of increased ethanol production. So we will come to a level that this glutathione are being depleted. So it's being used a lot. It's like being abused because of increased production of this acetaldehyde. And you could also say that it could interfere with lipid and VLDL production here. So I just summarized it by it could also accumulation of acetaldehyde lead to increased glutathione reaction trying to defend against oxygen species or reactive oxygen species. And because we are using this glutathione so much, what will happen? These reactive oxygen species will just be left without anyone defending against them, and it will lead to cell necrosis as well. And this is just what I was trying to mention right here. So I think I've covered everything through. So okay, I didn't talk about this reaction good actually. So in the microsomes you have CYP2E1, which will then create this NADP. Also in the cytosol you have ethanol reduced to acetaldehyde, and from acetaldehyde in the mitochondria we have production of acetate, and acetate through circulation creating acetyl coenzyme A and ketone bodies and TCA. We also have in the peroxisome hydrogen peroxide are being reduced or oxidized by catalase producing water molecule here. So this I think should cover everything for this topic at least. I think I've talked about everything and covered everything, and let's move on to the seminar task.